Today I wanted to open up by quickly reviewing the calculation of the cross product. If we have two vectors in R3, cross product is going to be an R3 thing for us. U cross V is a vector perpendicular to U and perpendicular to V. This is useful because it helps us describe a plane with one vector. So U cross V is a vector normal to the plane containing U and V. This is useful. We can now describe a plane with one vector. So we can describe some kind of orientation on a plane. Looking ahead, we're going to use tangent planes to describe surfaces locally, in the same way that we use tangent lines to describe curves locally. So U cross V is a vector normal to a plane containing U and V. These two statements say the same thing. This statement here is remembering how to calculate U cross V, and then down below is where that calculation comes from. The vector U cross V is the determinant of the 3x3 matrix with rows I, J, K, then the row U, and then the row V. How we calculate the determinant with cofactor expansion is that the first term in our cofactor expansion, you take out the first row and the first column, and these four entries left over. That's the determinant of that 2x2 matrix is going to be the cofactor, or is going to be the coefficient of I. So you do U2 V3 minus U3 V2. So U2 V3 minus U3 V2. A lot of times we present the determinant of a 2x2 matrix as just this handy little formula for that we do differently than all the other determinants. It is not different. It is the same thing. If we expand across the first row, we take out the first row and the first column, and we have the cofactor. The cofactor for U2 is just the scalar V3. So there's U2 times V3. Then we go to the next term. We alternate signs because we're calculating a determinant, and calculating determinants is one of the most voodoo math things that we do. There are reasons, but we never get into them when we first learn about determinants. Sometimes that happens in math. Then we go on to the next column, and U3, we take out the column and the row containing U3 and multiply by U3 by the determinant of its cofactor, which is just V2. So U2 V3 minus U3 V2. And then the same thing goes across. Now I wrote this in the other order here, so I did a UV, UV. So the subscripts went 2, 3, 3, 2. If you go UV, VU, then the subscripts will go 2, 3. Oops, these are backwards. See, this is why I shouldn't do this at 8 o'clock in the morning. If you change the order of the 1, 3, 1, 3, 1, 2, 1, 2. UV, VU, UV, VU, UV, VU. Trouble with holding two ways of doing things. Having more than one way of calculating something is a good thing because there's more than one way of calculating something. Having more than one way of calculating something is a bad thing because sometimes you'll just smash the two together. So you either keep the numbers in order and change the order of the U's and the V's, or you keep the U's and the V's in order and change the order of the numbers. So this is also U2 V3 minus U3 V2. This one in the middle could be a U1 V3 minus U3 V1. And the k can be u1 v2 minus u2 v1. Now you may be thinking, dude, we got this. You went over it in excruciating detail yesterday. Why so much excruciating detail today? Because repeated excruciating detail, it's actually multiplicative. It's excruciating squared. It's not 2 times excruciating, it's excruciating squared. But the reason for that is songs don't get stuck in your head because you hear them once. Songs get stuck in your head because they won't stop. All right, let's talk about where the normal vector shows up in a plane. So we had a couple of ways we represent planes. Remember that any two non-collinear vectors define a plane, and we can also define a plane as everything perpendicular to one vector. Any two non-collinear vectors can define a plane. This is where we might say the plane containing u and v. The plane containing u and v. We can also define a plane as everything perpendicular to one vector. So a normal vector defines a plane. Here we're defining the plane as using what is definitely not the plane. We're with the plane containing u and v, we're describing what is the plane. By saying the plane is everything normal to this vector, we're saying what the plane is not. We have 2 ways to define a plane. There are 3 dimensions running around in R3. We can either say the plane is these 2 dimensions, or we could say the plane is not this one. So we're describing the plane in a couple of different ways. What the plane is, or what the plane isn't. We're describing the plane as what the plane is or what the plane isn't. 2 ways we can describe a plane. It's a little bit glib to be like, oh, what the plane is and what the plane isn't. So we're either using describing the plane as stuff in the plane, using stuff in the plane, or by saying what stuff is not in the plane. We don't always get to define stuff this way. It's pretty cool that we can, because this is the case where everything in R3, if we have a plane in R3, everything in R3 is either in that plane or not in that plane. There's no in between. It's like, well, it could be both. None of that's happening. We can actually define something by what it isn't. We can't do that like with the real number line, right? We can't just divide the number line up into positive numbers and negative numbers, because 0 is like, oh, I'm neither one of those things, or am I both of those things? I'm special is what I'm saying. I'm like, oh, shut up, 0. Just because you're so important doesn't mean you need to throw it in our face all the time. Then I looked at the 0 and I'm like, oh, don't look all shocked at me. And then I realized that that's just what it looks like. So I felt bad. So we have a couple of ways to describe a plane. We know that one of the ways we describe a plane is in a function style, a plane containing a point x naught, y naught, z naught, with slopes m and n. We'll say z, we're describing as a function of two variables. A surface in R3 is going to be z naught plus m times x minus x naught plus n times y minus y naught. In this scenario, m is going to be the change in y divided by the change in z divided by the change in x. At this point, I don't have to switch to partial derivatives like we're going to next week, because we have a linear function and the rate of change will always be the same. Next week, this delta z over delta x is going to have to become a dz over dx when we start putting tangent planes onto surfaces at points. But that's just what we call in the business foreshadowing. Like, drop a hint as to what's coming next week. I probably should do it at the end of class, at like in the middle of wrapping up. That's called a mid-credits sequence or a mid-credits scene. So like in the middle of the credits, I preview what's coming next week. The problem with doing that here in class is that I go into the wrap-up voice. I can't do an example of it because you'll instinctively leave the class. If I start using wrap-up voice now, you'll just start packing everything up, right? So I can't go into wrap-up voice, very dangerous. But if I go into wrap-up voice, and then like in the middle of all that, then I'm like, oh, next week we'll be talking about partial derivatives. And then I can continue on with the rest. That's like a mid-credit scene. So because we're dealing with a linear function, our derivatives are always going to be constant. Oh, I shouldn't say derivatives. We haven't talked about those yet. See, now another character is like, oh, what's this about derivatives? Michael, don't worry about it. Until Avengers 2, Electric Boogaloo. I don't think it was called that. But since we have a linear function, our rates of change will be constant, so I can just express them as slope. I should say dy, shouldn't I? I spelled y wrong. I'm not even sure what counts as Avengers 2. Was that Age of Ultron? Is that the second Avengers movie? Here's the thing. You have so much time and attention and money in these movies and so much cultural zeitgeist in all these movies that started in 2008 and ran to, when was the last one? Endgame, 22 or 20? Anyway, like 12 years of movies. 12 years of movies. Multiple TV shows. 2019, thank you. 11 years of movies. That's still a whole lot. And there's like what, 1,000 of them? There's like 1,000 Marvel movies. I barely remember any of them. This is why it's funny. I keep joking. It's like, oh, I'm gonna make this class into like TikToks and everything will just be a minute at a time, right? Just learn calculus a minute at a time. And yeah, we could all just kind of like watch it, but none of that matter. It doesn't sit. It's a great place to start. Now I realize that when you come to class and I'm performing live, it might as well be a video. I'm doing the same thing. I'm just presenting information and asking you to do it. But that's not where you figure stuff out. You figure stuff out by going home and doing thousands of problems. And that's what we don't want to happen. And it's very reassuring to us that when we watch like a 3-minute video afterwards, we feel super informed. But when we're called upon to apply that knowledge, we don't really have it because we haven't done the unpleasant work that is the work we need to do to acquire knowledge. Does that make sense? I think I put it this way before, but I have watched a lot of baseball in my life. You know what I can't do? Play baseball. Because you know what I haven't done? Is play baseball. If I wanted to become a better baseball player, you have to get out there and play baseball. You can't just watch some dude talk about hitting or fielding or pitching or whatever. You know what I mean? And yet students are still just super mean to themselves. They watch some dude do some problems one time, and then they think they can't do it when they look at their homework and they're confused. That's why I like to remind you, when you look at your homework for the first time, you're fucking supposed to be confused. If you're like, oh, whoa, this doesn't make any sense, you should be like, oh, whoo, I am relieved. Anyway. So a plane, one of the ways to describe a plane is as a function, because we opened up by describing functions. We opened up by describing surfaces as functions. The other way we can describe a plane, we can take this point slope, well, kind of a point slope equation, and we can just rewrite it. We can just hit it with the algebra stick, rearrange it into the standard form. We can just algebraically rewrite our linear function to be in this standard form, where I have x term, y term, z term equals constant. Instead of having this solved for z, have an x term, y term, and a z term equals some constant. When we describe the plane this way, we can still read what's going on. We can say this plane contains the point x naught, y naught, z naught. When we look at the equation of a plane in standard form, We see it contains the point x naught, y naught, z naught, and the coefficients of x, y, and z will be the components of a vector normal to the plane. Let's write down a plane, the standard form of a plane. Oh, I got 2 1s. So I got 1, 2, 3, 4, 5, no 6, and then there's a 7. That'll work. Oh, I should replace the 7 with 6. No, I don't. I'll leave the 7 as a 7. I'm going to divide by the 2 and the 3, and I don't want it to cancel out. That's right. I picked 7 because I don't want it to cancel out. Or do I? No, it's fine. It's fine. It's fine. Everybody here can handle that, right? Some of you are like, oh, I don't know. Is there going to be a quiz on fractions? And I'm like, oh, no. And then, yeah, we can handle fractions. So what we can see just by looking at this standard form is that there's a point on this plane at -1, 4, -5. So this plane contains the points -1, 4, and -5. I needed 0. That's why I shouldn't be allowed to have 8 o'clock classes. I wanted this. So this plane contains the points -1, 4, 5, and we have a normal vector This is the description of what's going on in the plane. Now we need to learn how to use this information. If we want to find other vectors in this plane, we can just plug in more points. Plug in an x and a y and find a z, and then we'll find another point on that plane and connect a vector from a point that we know is on the plane to another point that we know is on the plane. So if we want to find a vector in a plane, so if we want a vector in this plane, one thing that we can do is find a couple of points on the plane and make a vector. So to find a vector on the plane, one thing that we can do is just connect 2 points on the plane. We find 2 points on the plane and just Google map our way from one point to the other by subtracting their components. That will give us a vector sitting in the plane. Finding points on the plane, we can choose an X and a Y and figure out what Z has to be on that plane. Because we know that a plane will be everywhere in R3. So for any 2 coordinates, we will be able to find a third coordinate. So if we want to find a point on the plane, we plug in 2 coordinates and find the third coordinate. The plane is going to be everywhere. For any X and Y, we'll have a Z. Or for any X and Z, we'll have a Y. For every Y and Z, we'll have an X. If we want to plug stuff in, if we're going to be plugging in X's and Y's, we might want to rewrite the equation in its function form by solving for Z. So if I want to get my equation in the form of a function, so like in a point, slope form, then all we have to do is solve for Z. This will tell us a lot of information that we find interesting anyway. So in this equation, that's why I put a 1 there, because I'm lazy. So if I wanted to solve for Z, we'll put the X and Y terms on the other side. So I'll have the +1 times Z minus Z plus 5 is equal to a -2 times X plus 1 plus 3 times Y minus 4, and then divide by the 1 and subtract 5. So Z is equal to -5 minus 2 times X plus 1 plus 3 times Y minus 4. So we can see Z starting at -5 and decreasing by 2, starting at -5 when X is -1 and Y is +4. And we can see Z decreases by 2 when X increases by 1, and Z increases by 3 when Y increases by 1. We can see the slope in the X direction and the slope in the Y direction. Now it's easy to find points on this plane. Once we have 2 points on the plane, we can write vectors on the plane, and then we can confirm that 2, -3, 1 is normal to the plane. Any questions? These are all the same things that we could do with lines. We had 2 points, that defines a line, and we found the equation of the line connecting those 2 points. Find the slope of the line, use the point slope equation, rearrange it into the standard equation if we wanted a vector perpendicular. Then in standard form, the coefficients of x and y will be a vector perpendicular to the line itself. All the same stuff, except that the linear equation in 3 variables defines a 2-dimensional plane in R3. We happen to be able to define that surface with a function, just like we could with a line. Any questions? How's everybody? Okay. To bring it back to a calculus thing, the reason that we care about planes is that we use planes to describe surfaces. We use planes to describe surfaces, just like we use lines to describe curves. Just like we use lines to describe curves, we want to use planes to describe surfaces. We use linear stuff to describe nonlinear stuff. So we use lines to describe or analyze curves. We use planes to describe. I'm going to throw in analyze surfaces. The game that we're playing is we're taking nonlinear stuff and describing it with linear stuff. Standard calculus maneuver. Use linear stuff to describe nonlinear stuff, because if we look close enough, everything looks flat. If we look close enough, everything looks flat. When you zoom in enough, everything looks flat. Oh, everything continuous looks flat. I don't want to be haunted by the ghost of Weierstrass. Fools that everything looks flat. Shut up, Weierstrass. You know what I meant. Any questions? Comment? Side remarks. Everybody looks stunned. You all look like this. You made it through. This is the 3rd Friday. You made it through 3 of the, I think, 16. I think there's 16 Fridays. 3 of the 16 Fridays. By the end of week 3, it really starts to sink in. Every day. At 8 o'clock. At 8 o'clock. Until December, early December, last 8 o'clock meeting will be December 8th. That's good news, right? No, no one looks happy because it's just September 1st. All right. That's going to do it for today. You should be working on chapter 13. The chapter 13 homework is your current project. Next week, since we're talking about like lines and planes and all this stuff, and I definitely implied that's going to come up because I wrote stuff like dz dx and dz dy, derivatives are going to be coming up. The good news about partial derivatives is that you already know how to find partial derivatives. There's nothing new that we have to do. You're going to take what you know and do that. In fact, you're going to take what you know, ignore some stuff going on, and just find partial derivatives. I promise you, you already know how to find partial derivatives. You actually already know how to interpret partial derivatives. So if you're not, then you're just kind of pretending that you don't, because you want me to spend more time on it because it puts off when the homework is due. I see your game, you rogues. That's going to do it for today. I'll see you all on Tuesday. Everybody have a good long weekend, and thanks for playing.